Welcome friends. In this class we are going to deal with the scattering of light. We know the phenomenon of light, that is reflection and refraction. I am going to explain how reflection and refraction completely different from scattering of light. See here, these particles in the atmosphere can be called as scatterers because the light rays when enter into the atmosphere, then these particles scatter light, and these particles can be called as scatterers, and the phenomena of refraction can be called as scattering of light. Now, see the definition. When sunlight enters the Earth's atmosphere, the atoms and molecules of different gases present in the atmosphere refract the light in all possible directions, and this is called scattering of light. Let me explain more about scattering of light. See here, in the atmosphere, you take a scatterer. When the incident ray incident on the particle, then it will be scattered in all possible directions. See here, the particle is stationary. It is not like that I am taking a particular instant for the illustration to be very effective. In this molecule also moving as that of the other molecule in the atmosphere. When sunlight enters into the atmosphere, then hits the molecule, after that it will be scattered in all possible directions. Let me explain types of scattering. Depends on the initial and final energy of the light beam. Scattering can be classified into two categories. One is elastic scattering and the other one is inelastic scattering. When a beam of light interacts with a constituent particle of the medium, then it undergoes many kinds of scattering. So, we have to take into account the initial and final energy of the light beam. Now, let us explain how elastic scattering takes place. See here, this is the model of elastic scattering. You take a scatterer when initial energy E1, when a light ray of initial energy E1 interacts with this particle, then if you calculate the final energy of the refracted ray, then you can get E1 equal to E2. Elastic scattering is mathematically expressed as E1 equal to E2. That is, the initial energy E1 equal to the final energy E2. This type of scattering can be called as elastic scattering. But reverse is the case in the inelastic scattering. In the inelastic scattering, if you calculate the energy E1 and energy E2, then it won't be the same. There is some differences in the energy E1 and E2. In the case of inelastic scattering, reverse is the case. That is, this is the incident ray which possesses the initial energy E1, and if you calculate the energy of the refracted ray, it is E2. If you combine these two, then E1 not equal to E2. And this type of scattering can be called as inelastic scattering. Depends on the nature and size of the scatterer, which results in different types of scattering. They are called Rayleigh scattering, Mie scattering, Tyndall scattering, and Raman scattering. Let us explain one by one with some illustrations and examples. Rayleigh scattering. When light rays incident on a scatterer, then it will be scattered in all possible directions. This is same as that of the definition of the scattering, but Rayleigh scattering is expressed with a mathematical expression. And now let us define what is Rayleigh scattering. See here, Rayleigh scattering, the scattering of sunlight by the atoms of molecules of the gases in the Earth's atmosphere is known as Rayleigh scattering. I will read once again. The scattering of sunlight by the atoms or molecules of the gases in the Earth's atmosphere is known as Rayleigh scattering. And Rayleigh scattering can be explained with the help of a mathematical expression. That is, the amount of the scattering, which is denoted as S, is equal to 1 by lambda power 4. That is, the amount of scattering of light is inversely proportional to the fourth power of its wavelength. And this is the statement of Rayleigh scattering. Let me explain Why sky appears as blue? When sunlight passes through the atmosphere, the blue color is scattered to a greater extent than that of the red color. Red color possesses longer wavelength, but blue color possesses shorter wavelength, and this scattering causes the sky appear in blue color. I'll repeat once again. When sunlight passes through the atmosphere, only the blue color scattered to the great extent than that of the red color, and hence sky appears in blue color. This example will help you more to understand why sky appears in blue color. We can say that the shorter wavelength colors are scattered much more than that of the longer wavelength colors. Blue color comes under shorter wavelength range and so scattered more than that of the other colors, and hence the sky appears in blue color. I'll explain why sun appears in red color during morning and evening. At sunrise and sunset, the light rays from the sun have to travel a larger distance in the atmosphere than at noon. Hence, most of the blue light are scattered away and least scattered reaches us. Therefore, the color of the sun is red at sunrise and sunset. And this illustration will be very helpful for you to understand more. During morning and evening, the sun rays from the sun have to travel larger distance in the atmosphere. But at noon, it is not like that. Sunlight travels only shorter distance to reach the Earth atmosphere. So, most of the blue light scattered away and only a red light reaches us. Therefore, the sun appears red during morning and evening. Next one is Mie scattering. Large particles in the atmosphere are able to scatter all wavelengths of white light. That is, when all wavelengths of white light are scattered equally, then Mie scattering is occurring. Mie scattering takes place when the diameter of the scatterer, see here, the diameter of the scatterer is similar to or larger than the wavelength of the incident light. When the diameter, that is d, is equal to or greater than that of the wavelength of the incident light, then Mie scattering occurs. Examples of Mie scattering. Why clouds appear white? Did you ever find the answer? And I will explain you why it is happening and what are the reasons behind it. When you compare atmospheric particles with that of the particles in the cloud, then you can easily find that the particles in the cloud are larger than the atmospheric particles. And we know sunlight is white, that is combination of all colors. When sunlight passes through the cloud, the light rays scattered by water droplets almost equally or simply they scatter all colors equally, and these again combine and produce white color. But behind clouds we see blue color because the size of the atmospheric particles is smaller than that of the cloud particles, and that's why the sky appears blue and the clouds appear white in color. This is the important scattering, Tyndall scattering. We know that dust particles present in the atmosphere, and also our globe is full of dust. Consider a beam of sunlight when it enters into a dusty room through the window. This is due to the phenomenon of scattering. The dust particles present in the atmosphere scatter the beam of the light, and so we can easily observe the path of the light. And this is Tyndall scattering or Tyndall effect. You can expect the same phenomena in colloidal solution also. You know, colloid is a microscopically small substances that is equally dispersed throughout another material. Examples are milk, ice cream, smoke, etc. See here, this is the true solution, and this solution is a mixture of water and milk. And when you pass a flashlight through these two solutions, then you cannot observe the path of the light in the true solution, but it is visible in the case of the colloidal solution. When you pass a beam of light, then in this true solution you cannot observe the path. Rather, in colloidal solution, the path is visible. This is due to the scattering of the colloidal particles with light and hence explains the Tyndall effect. Raman scattering is one of the important scattering effects. Raman won Nobel Prize in 1930 for physics. He discovered the Raman effect. Besides discovering Raman effect, he studied extensively in X-ray diffractions, acoustics, optics, dielectrics and colloidal solutions. Consider a beam of parallel monochromatic light. Here, monochromatic means light of single wavelength. Laser light is the best example for monochromatic light. You take any medium, which may be a gas or liquid or transparent solid. When you pass monochromatic light beam, then the light will be scattered. But it was observed that the scattered light contains different frequencies or wavelengths, or simply we can say that the scattered light contains some additional frequencies other than the incident frequency, and this effect is termed as Raman effect or Raman scattering. Then what is a Rayleigh line? The spectral lines which are having same frequency as that of the incident ray are called as a Rayleigh line. Here you can see a Raman line. Suppose the scattered line contains frequencies other than the incident radiation, then they are termed as Raman lines. Rayleigh lines having the same frequency as that of the incident radiation, but Raman lines possess frequency other than the incident radiation. So I indicated the arrow mark with a blue color. But if you look at Raman line, then the arrow marks are indicated with different colors, that is yellow and orange. And this indicates that they are having different frequencies other than the incident radiations. Now coming to Stokes lines and anti-Stokes lines. If you calculate the frequency, then for Stokes lines, then the frequency will be lower than that of the incident frequency. But if you calculate the frequency for anti-Stokes lines, then the frequency is higher when you compare with that of the incident radiation. And so they are called as anti-Stokes lines and Stokes lines. Depends on the frequency or wavelength, the lines are categorized into two types. One is Stokes lines and the other one is anti-Stokes lines. Thank you for watching, friends. If you want to improve our promotion of more videos, comment in the comment box and suggest us more and more to enlighten the concepts in science. Thank you.